Hello and welcome, hopefully, welcome back to the latest in OpenEye Cadence Molecular Sciences series of webinars on computational chemistry and computational drug discovery. My name's Paul Hawkins, Principal Product Evangelist here at OEC-NS, and I shall be your host for today's presentation. I'm delighted to have as our speaker today Dr. Chris Neale, the head of our Molecular Affinity and Selection Group. Chris's title, very interesting, Too Hot, Too Cold, or Past Midnight. Chris, as I said, is the director of our head of our affinity selection group, and he comes to us from just up the road at Los Alamos National Lab, very close to our HQ here in Santa Fe. Chris's interests primarily revolve around method development for structure-based design, cellular signal transduction, and as you'll see a little bit of today, uncertainty quantification. Before I turn the proceedings over to Chris, a small note on housekeeping. If, as I hope you will, you have questions during the course of the webinar, please put them in the chat section of the webinar interface. We will have a Q&A session at the end of the talk. If we do not get to your question during the Q&A session, we will respond to your question as soon as we can by email after the webinar is over. So, with that housekeeping note, Chris, it's all yours. Take it away.
Thank you, Paul. Making good choices about which molecules to make next is a key driver of success in lead optimization. And these choices start with ideation. These are the molecular embodiments of your design hypothesis about what underlies affinity and activity. And when your goals are to increase the binding affinity or to hold it constant while you're optimizing other properties, then physics-based relative binding for energy computations can add a really valuable approach to make the decisions about which molecules to make and which ones not to make in your next synthesis cycle. I'm going to introduce our tool for this, which is free energy non-equilibrium switching, or FE-NES. Then I'm going to talk about the balance that always exists between how much compute we invest per calculation, in an attempt to try and drive toward higher accuracy, but on the other hand, how many molecular variants we can assess in a design cycle, because there's always a tension between those two desires. I'm going to do this first in a high throughput synthesis regime, where we're looking at weeks or a small number of months to get your hands on these molecules and a few $100s per molecule. And then I'm going to close with an evaluation of how this changes, and in fact, whether this changes in a high cost synthesis regime where we're talking about many months and perhaps tens of thousands of dollars for those new molecules to be made and then evaluated. The binding free energy is a direct measure of the strength with which a molecule binds to its protein target. What we'd really like to do is to take a series of small molecules and look at the free energy that's released as they move directly from the unbound state to the bound state, and then we could just compare them and rank order them via that measure. And it turns out that computationally this is particularly challenging. So what we do instead is we take the bound state of a small molecule, say molecule A, and in place we morph it alchemically, so unphysically, from molecule A into molecule B, and during that process we assess how that changes kind of the stickiness, the binding strength of that molecule to its protein target. So if molecule B is the stronger binder, then morphing alchemically from molecule A into molecule B will release more free energy in the bound state than it does in the unbound state. And we just calculate those values, we take the difference, and that's our then quantitative estimate of the difference in binding free energy between those two molecules. So in order to compute this, we have to run simulations, molecular dynamics simulations of both of those end states. So on the left, we've got an example of a molecule A, and on the right, molecule B. We're testing the hypothesis of whether adding this particular hydroxymethyl can enhance the binding affinity, presumably by making some type of direct interactions with the protein. So we need to simulate these end states, but we also need to simulate intermediates. And we need to do that so that we can assess the change in free energy as you move between those end states. So the simulation of end state B, this has the hydroxymethyl fully engaged with the protein in this case. These are the protein ligand interactions that help to enhance the binding affinity of this lead series. And on the left, in molecule A, we actually have this hydroxymethyl present, but it's non-interacting. And the reason that we have to have it there is to provide a handle so that we can morph from molecule A to molecule B. But on the left, that hydroxymethyl is not forming favorable interactions with the protein. There's no energetic benefit, and its conformation reflects that. It's free to move. In the middle, then, so this would be kind of halfway between molecule A and molecule B in this non-physical chimeric construct, we have partial strength protein ligand interactions between the growing group and the protein. We also have partial water displacement. So this over time, as we move between molecules A and B, this group gains the ability to displace more and more water. And we have persistent valence terms. And that's so that this group doesn't fly off into another region of the simulation cell during our alchemical changes. So this can be done by slow simulations that attempt to approach equilibrium. FE-NES attempts to do this in a non-equilibrium method because there's many cloud advantages of that type of approach. So what we do is we take our system with ligand A bound to the protein, we run it for 6 nanoseconds of standard MD, and then we collect a set of frames from that trajectory. Here, 80 frames. That's now an ensemble of configurations that reflects the ways that ligand A can interact with the protein on that time scale. And then we're going to drive these non-equilibrium switches very rapidly, over 50 picoseconds. Ligand A becomes ligand B. We do that 80 times, and by integrating the force of this, we appear the hydroxymethyl group, and we get an estimate of the free energy difference between those two ligands in the protein binding pocket. So not only are we changing essentially the force field and the types of interactions that can form as we drive this switch, but the system has to respond. The conformational ensemble has to change. We need to see the engagement of that hydroxymethyl with the protein backbone, not in every switch because this is a non-equilibrium method, but we do have to see it sufficiently many times that we can get an estimate of the affinity change that occurs during that process. So this is the example where we're going to appear the hydroxymethyl. We also run end-state simulations of ligand B, which has the hydroxymethyl, and then 80 driven switches that vanish that hydroxymethyl. We do this in the bound state. We do both of these sets of simulations in the unbound state, and combining all of that gives us our estimate of the difference in affinities between ligand A and ligand B for that target. So it's important to note that we don't actually need any experimental affinities to take these relative binding free energies and assign ligand-specific binding free energies that can be used to rank order these molecules for prioritization. So if we don't have any experimental affinities, we can just set the binding affinity of one of them, say molecule A, to some constant or 0, and then we can use the differences between A and B, A and C, A and D to generate a set of ligand-specific binding affinities. We can do this with as large a map as one wants, and the only difference between this and the estimate that you would get from either an absolute binding free energy or from evaluating this set with at least one known experimental affinity is there'll be some constant offset, but the relative differences and the ranking will be exactly the same. So we ran FE-NES on 20 different protein ligand benchmarks. 8 of them are from Lingle Wang's 2015 paper. 8 are from Christina Schindler's 2020 paper, and we collected another 4 from the literature. And I'm showing each of these 20 targets horizontally with a bar that represents their Kendall's tau. So that's a measure of the rank association between the FE-NES prediction and the experimental affinity. This measures our ability to rank compounds and prioritize them for synthesis. For Kendall's tau, the maximum value is 1, and 0 would represent a random distribution of predictions. You can see that we've got 14 of these 20 with a Kendall's tau above 0.4. That's where this prioritization begins to be useful for decision making. And 8 of the 20 have a Kendall's tau above 0.6, which is where we get into much more robust type of prioritization. And the really interesting thing was that we ran this again with a quarter of the sampling. So we asked, what if we didn't do 6 nanoseconds per end state and 80 switches per edge, but instead we ran 1.5 nanoseconds of simulation per end state and only 20 switches. And that's what's shown with the pink bars, which are very similar in their ability to rank order ligands in these series versus the blue bars, which is our default approach, which uses 4 times more computational sampling. And this is really going to motivate the middle part of this talk. Before I get to that, I just want to highlight one of these examples. So this is the CDK8 test set, and these are the scatter plots of horizontal experimental affinities versus vertical FE-NES predictions that I used to compute Kendall's tau and show on that plot. That was CDK8 was one of those 20 sets. And on the left, we've got with default settings, you can see we've got not a perfect correlation, but a ability to prioritize ligands. And on the right, we've got a similar Kendall's tau and R squared and mean absolute error. The predictions are different. The uncertainties on our predictions are larger, but we're only using a quarter of the sampling, and we're still getting a useful ability to rank order these small molecules. So the question then is, how do we balance this? Because if I put less sampling per molecule, then I can assess more molecules with a fixed compute budget. And we're going to do this first in a high throughput synthesis regime, a low cost synthesis regime. If I told you that evaluating more analogs with a fixed prediction error would lead to better outcomes, I presume that nobody would object to that, right? Because when we evaluate fewer analogs, then everything that we've triaged out with a simpler method is invisible, right? We've already gotten rid of it. We can't then identify it by a physics-based approach as a strong binder. So more analogs, fixed prediction error should give us better outcomes. It's also true that if we have a fixed number of analogs, but we drive down that prediction error, we have more accurate predictions, we should also be making better outcomes. In the extreme, our predictions are perfectly rank ordering, and we are then going to make the best molecule of the set that made it into the final stage of predictions. But both of these come with an opportunity cost. Both of them are saying, well, if I throw more compute at this, I can get better outcomes. And that's true. If you have extra compute, these are both good things to do. But at some point, I'm going to have new ideas on this series. I'm going to have another project that I need to work on tomorrow. And there's an opportunity cost to just continually increasing the amount of compute that we use in the final stage of our triage funnel. So the more interesting question is, what if I set a fixed compute budget and I look at that balance between the number of analogs that I can evaluate and the amount of compute that I spend on the prediction per analog, because more compute in general will drive down that prediction error, making them more accurate. So I'm going to start this with an evaluation of a set of 10,000 congeneric small molecules from TYK2 inhibitors. This was a relative binding for energy study from Relay Therapeutics and Google in 2022. I'm going to use these published free energy predictions as the ground truth for this statistical evaluation. And my approach is going to be to reach into that bag, grab some number n of small molecules. That's going to be my evaluation set. I'm going to noise them to create some error. This is going to be our approximation to some type of prediction error. And then I'm going to look at the top 100 recovery versus the full set of 10,000 ligands with no added error. And that's shown quantitatively on this heat map here for many repeat evaluations for different number of molecules that I selected. That's the horizontal axis. And then the noise that I added where the prediction error increased vertically. So in the bottom right of this plot, we've got perfect top 100 recovery. We evaluated all 10,000 small molecules. We didn't add any prediction noise. And our top 100 is exactly the top 100. If I then look at only, say, 5,000 molecules, with no prediction error, I should actually only be able to recover 50 of the top 100 in my top 100 because I triaged out 5,000 of them that become inaccessible then to my RBFE-based approach. Also, if I stay on the right side of this with looking at 10,000 molecules evaluated, as I go up on this plot, I'm getting lower and lower top 100 recovery because my predictions are not as good. I'm not ordering them via the noised prediction in the same way that they're ordered with the ground truth in this case. So if I'm somewhere on this plot, and this plot exists in all situations, typically we have no idea what it looks like, but there is a landscape there. If I exist at this point X, it's always going to be true that I can make equivalent or better decisions if I drive straight down. Drop my prediction error. That's one thing I told you before. I make better decisions for the same number of molecules evaluated if I can have more accurate predictions. That's something that we could do by increasing the amount of compute per RBFE edge. We can also make better decisions by going to the right on this plot, where we are evaluating more molecules at the fixed prediction error. And in fact, everywhere in this lower right quadrant should be better outcomes. This is also a regime where we have increasing opportunity costs, because we're talking about just adding more and more compute to get better outcomes, which has value, but it has opportunity cost. So another way that we can look at this is this dashed black and yellow line is now one of the isocontours along which the outcomes are equivalent. I'm getting the same amount of top 100 recovery. And clockwise to this point, I should always be making better decisions. Counterclockwise, I should always be making worse decisions. And then the question is, how do I assess my the goodness of my outcomes when I don't know this underlying energy landscape, and I'm considering evaluating more molecules by using less compute per edge, which I predict and expect to somewhat increase my prediction error. So we're going to assess this with a synthetic data model. We do this because it gives us access to multiple repeats, and we can generate very large data sets. These 20 data sets I showed you before had 10 to 50 small molecules, and we're not as interested in asking, should I make predictions on 10 or 50? We're more interested in asking, should I make predictions on 100 or 500 or 1,000 or 5,000? So what we did was we took our actual FE-NES predictions and the actual experimental values and used that for Gaussian property matching. So we matched in this synthetic data the experimental mean and distribution of affinities. We also matched the prediction error and the correlation of the prediction error with the experimental values. So I'm going to show you an example of this. This is for the beta secretase 1 set. This is the actual data, so the real experimental values per ligand horizontally and the real FE-NES predictions vertically. Got a Kendall's tau of 0.55. It's a useful regime for prioritizing molecules for synthesis based on the FE-NES predictions. But we've only got 36 molecules here. So with this property matching, I can create below this easily a synthetic set of 10,000 small molecules, where now I have synthetic experimental values and synthetic FE-NES predictions for each. But because it's property matched, I get the same Kendall's tau, R squared, and mean absolute error. And we're going to use these sets then to assess how the change in the amount of sampling that we invest per edge combined with a change in number of small molecules affects the goodness of our outcomes. So this is the experiment. I'm going to create n synthetic analogs. Each will have a synthetic experimental value and synthetic prediction. And then I'm going to imagine that I will make and experimentally evaluate the top 20 of those by prediction. So I'm going to use the synthetic FE-NES prediction to select 20, and then I'm going to look at the top experimental value within that set. So essentially what I'm saying is I'm looking for an improved affinity lead. I'm going to make 20, and if one of them is better, I'm happy, and I'm more happy the better it is. So this is a worked example of this. Here I made 500 synthetic analogs. I'm showing horizontally the synthetic experimental value and vertically the synthetic FE-NES prediction. Again, this was parameterized to property match our actual beta secretase 1 FE-NES predictions. So I've got 500, and then the lower 20, most of which are in blue, those are the ones that have the strongest affinity according to the FE-NES prediction. That's all I'm going to make. And then within that, I'm going to take the one that's furthest to the left, that's shown in red. That's the one within the top 20 predictions that has the top experimental synthetic value. And that's a single number that I'm going to report for that n and that property matched noise fitting. And I'm going to repeat this 1,000 times at different values of n. So you'll notice also that there were 4 better analogs, and those don't show up in the result because the prediction wasn't perfect, and our synthetic data reflects that. So we missed out on 4 better analogs because we We didn't decide to make 500. We used this to triage and make 20. So here's the outcome of that if I fix the prediction error. This is where I'm going to increased opportunity cost to evaluate more and more ligands. And this shouldn't surprise anybody. My outcomes get better. The best experimental affinity in that set that we imagined that we made gets better. It becomes a larger negative number. It goes down as we go from the left to the right, increasing the number of synthetic analogs. So the circle in the middle is the average across 1,000 repeats, and the bars enclose the 95% confidence interval. But I said I wanted to do an evaluation at a fixed compute budget. And to do that, we need one more piece of information, which is the relationship between the data and the computational expense of generating that data. So what I'm showing here is from left to right, I'm decreasing the number of switches. So 80 switches after 6 nanoseconds of end-state sampling is our default on the left, and then 40 switches after 3 nanoseconds of sampling, or 20 switches after 1.5 nanoseconds of sampling. And on the left, you can read out the change in the number of ligands that I'm able to access. So if I can do n ligands, maybe 500 at our default settings, for the same computational budget, if I run only 20 switches per edge, I can run 3n, or in that case, 1,500 ligands. And it's not 4n because there's some overhead to all of this infrastructure, but that's the trade-off. I'm going to look at putting in 1/4 of the sampling per edge, which allows me to assess 3 times the number of ligands. And of course, I said that comes at a cost. So this is just an example for beta secretase 1. As I invest less compute from left to right, my mean absolute error of my predictions in my actual FE-NES predictions is flat for a while, and then it starts to go up. We get about 0.2 or 0.25 kcals per mole of additional error, and then it really starts to go up when we move to very little sampling. So now that I've got this information, I can go back and look at beta secretase 1 with that trade-off between compute invested per ligand and number of ligands, and I'm doing this with property matched error. So when I go from 80 to 20 switches, I'm generating new synthetic data that's fitted on FE-NES runs from either 80 or 20 switches. That's how I incorporate the information about the reduction in prediction accuracy as I move to less and less compute per edge. So on this plot, on the bottom axis, we've got the number of switches. That's the compute investiture. It's going from 80 on the left, decreasing to the right. On the top, you can see the number of analogs that I'm able to evaluate at a fixed compute budget, given that investment per edge. So 20 switches here is 1,500. If 80 switches is 500. And again, you can see the outcomes are improving as we move from left to right. As we start to evaluate more analogs, then we get better decisions, even accepting that slight increase in computational error that occurs as we reduce the amount of computational investment per edge. So that was just for beta secretase 1. I did this for 16 different target series, and we fitted them independently per target ligand set and independently per amount of sampling per edge. I'm showing on the right Kendall's tau, horizontally the actual Kendall's tau from the real FE-NES predictions on 10 to 50 analogs, and vertically the synthetic Kendall's tau from sets of 10,000 analogs. And you can see that they fall pretty close to the diagonal, which implies that our synthetic data is capturing many of the linear properties of our actual predictions. And then we can look at this in the same way, but now for these 16 different data sets. So this is, again, with property matched error. This is the evaluation at a fixed compute budget, where I'm investing less compute per edge as I go from left to right, but I'm also evaluating more ligands as I go from left to right, and that's what you can see on the top axis. So you can look individually at each of these series, each of which is a different color, or you can just look at the average, which is shown by that dark black horizontal line. And we're seeing, again, better outcomes on average as we shift to the evaluation of more compounds at a fixed compute budget. On average, we've got about 0.5 kcal per mole of increased affinity, and there's a range there which ranges from even better than that to no improvement. The key here is not that we're just saying we don't need much compute per edge. We're saying if we run less compute per edge, we can evaluate more ligands. Many of those ligands are ones that we triaged out based on a much less capable scoring method because it was much faster and could be run on many more ligands. And so, when you move to the left on this, you're putting a lot of weight on the upper portions of your funnel. And as you move to the right on this, you're saying, well, let's bring more of those molecules down to our best method for predicting affinity. If I don't do this trade-off, if I just invest less compute, that's that red bar on the right, but I don't increase the number of analogs, as expected, we get worse outcomes. I get a smaller negative number, a more positive average for the predictions. Now, it's perhaps not as much worse than the bar on the left that one might expect, and that's for two reasons. The first is that, as I showed you for beta secretase 1 on a previous plot, as we run less and less sampling, the increased prediction error goes up rather slowly. The second reason is that I'm doing this synthetic experiment in a high throughput synthesis regime, a low cost synthesis regime, and that adds some buffer. Remember, I said I'm going to make 20 molecules and I'm happy if one of them is good. More happy, the better it is. I'm not actually measuring the 19, and we'll get on to how that changes in a high cost synthesis evaluation next. So I showed you in this segment that we can make better decisions by making predictions on more analogs, even when the prediction error increases modestly because we're putting less compute into each edge. Now, this does require that you have many similarly promising analogs. You can't take 500 good ideas and add 1,000 terrible ideas and expect to get better outcomes by making this trade-off. This happens when you've kind of set an arbitrary threshold. I can only afford to run physics based on 500, even though I'd like to run it on more. I think that's frequently the case, and that's the case in which shifting this balance toward predicting on more molecules can add value. I showed you that the trade-offs vary by the system, right? In some cases, we're getting 0.8 kcals per mole better. In some cases, 0 kcals per mole better. So this is the type of thing that one would want to evaluate as they move into different series or targets. And it probably differs, it almost certainly differs by the method that you're using. We use a non-equilibrium approach for FE-NES. If you're using an equilibrium RBFE approach, I suspect that you could get similar benefits by shifting this balance toward more ligands with less compute per ligand, but that's something that would have to be assessed directly. Okay, so those high-cost synthesis scenarios, the best way I can imagine to do this is to say, I can't afford to make 20, I can afford to make one. I'm going to get one shot on goal, and I really need it to be right. So I'm going to do the same thing. I'm going to create n synthetic analogs with property matched error, but I'm only going to make the top predicted compound, and then I'm going to report the experimental synthetic affinity of that compound. And as you can see on the right, the situation changes a little bit, right? We're no longer seeing this kind of robust improvement of outcomes as we shift towards evaluating more analogs with less compute per analog. We can look at another target. This is PTP1B. Here we are seeing some benefit as we go from 80 to 40 to 20 switches, which of course is 500 to 1,000 to 1,500 small molecules. But then it starts to come up. This is where we're not only seeing decreasing gains, but it's starting to reverse the preference, shifting back toward the need for accuracy when you kind of lose this buffering of let's make 20 and hope that one is really good. This is the analogous plot now for the one shot on goal approach. These are those molecules that are costing you a lot of money to make each. And you can see somewhat of a similar trend. The outcomes do start to get better as you go from evaluating 500 to almost 1,000 to 1,500 small molecules with the fixed compute budget. But then it starts to turn up at the end. The overall benefit as you go down to a very small number of switches, a very small compute investment per edge, it's lower at 0.3 plus or minus 0.3 kcals per mole. And we are now seeing some cases in which 5 switches per edge on almost 4,000 compounds is in fact giving worse outcomes than 80 switches per edge on 500 compounds. You can see a similar effect if we were to run less compute per edge on only those 500 molecules. So schematically then, right, to go back to this plot from the Relay and Google data, this is the plot where if we're at point X, everything in blue is better decisions and better outcomes. And what moving from the high throughput, low cost synthesis regime to the high cost, low throughput synthesis regime gives you is it appears to shrink this region of better decisions. So this isocontour would come clockwise and it shifts the balance, not all the way, but somewhat back toward the need for a higher accuracy in predictions when you only get one shot on goal. I think that's pretty intuitive, but this is a quantitative demonstration of that. So I showed you in this section that trade-off shifts back toward accuracy in the high synthesis cost regime, but not completely. There's still a benefit of evaluating more compounds at a fixed compute budget. It's also worth mentioning that in this, and indeed in the earlier regime, we can imagine stage triage where we're running on a larger number of molecules, we're running physics-based free energy calculations, investing less compute per edge, getting rid of the very worst, and then moving on to a higher accuracy prediction in a second phase of that triage. So I showed you in the first part of this talk that RBFEs and FE-NES is a good tool for triage and prioritization. I showed you that with that bar plot of our Kendall's tau values for 20 different series. I demonstrated that there's this tension between the cost per ligand and the number of ligands that we can evaluate, and that pushing more ligands down into our most accurate stage at the expense of putting less compute per ligand often improves outcomes. And then in the regime where you get very few shots on goal, that shifts back toward accuracy. Thank you very much for your attention. If you have questions, please reach out to us. Paul, I think we've got some questions queued up.
Chris, thank you. Fascinating. There's always a very different look at, I think, a way a lot of people think about RBFE methods. More can be better. So a few questions arising, sort of fairly obvious technical one to start with. What's the MD engine or tool that's underlying our FE-NES implementation?
We use both OpenMM and GROMACS. The tools offer various benefits. They're of similar speed. They both make good use of efficient use of GPU resources. In the actual FE-NES simulation, we're using GROMACS at the moment, but we're also exploring the benefits of other packages.
And then a related question, which I'm sure you could see coming. What's the force field, and does the force field have much of an effect on the accuracy or the quality of the results?
We're using an amber force field for the protein. This is FF14SB. We use the open force field, SAGE force field for the ligand, and PIP3P for the water. Absolutely, the force field affects the results. The amber protein force field has been developed over many decades. It can do things like fold proteins. Its side chain behavior is, in many cases, in good agreement with NMR data. So we're pretty solid on that front. In terms of the ligand force field, the open force field takes this approach of generalization and fitting to large amounts of solution data. So that gives broad coverage. It's a huge benefit to be able to simulate nearly any molecule that you can ideate and generate good behaviors for biaral portions and internal interactions versus protein ligand interactions. The balance of that is quite important, and that's all been taken into account in that parameterization.
So the OpenFF approach, being able to cover a large range of chemical space, really fits nicely with the large scale calculations you were speaking about earlier.
Yeah, not only being able to fit a large amount of space, but potentially not being overfit on the discrete sets where you've taken these small points out of this monstrous chemical space and refined to those specific points. It's a more generalized approach, which we believe has strong benefits.
Well, here's one that may take a little while to answer. It's quite a good question. I'll paraphrase. Why use physics-based methods when AI methods have been shown to be so successful for this topic?
I think AI methods have been shown to be very successful at interpolating among data-rich environments. And if you have that, by all means, a good interpolation can be a good prediction. The question is, when you start to look at things like unknown affinity cliffs or new series that don't have a lot of training data, be that either for the shape and features of the binding pocket or the chemistry of the ligand, there are a multitude of demonstrations that as soon as you get out of distribution, these AI methods will confidently give you very terrible predictions. So we should be using all of the tools in our kit. There are cases where a simple Gaussian process regression among your huge amount of data is the very best way to proceed. And there are cases where physics-based RBFEs simply can't be matched. And I think everybody probably does this, but I strongly believe the beginning of a project, run your RBFEs, run your AI models, run your MMPBSAs, run your Bose stabilities, and see what is working for your series. In more cases than not, that's going to be RBFE. We've done evaluations of a variety of methods, and yes, there are cases where a very simple measure is the best, but that's rare. The dominant best prediction method is for RBFE.
Very good. So certainly physics for the win in low data environments, and AI perhaps in certain higher data environments. Very good. Well, that was quite an answer, as I expected. So that's, I think, all the time we have for today. So Chris, once again, thank you very much. That was fascinating stuff.
Thank you, Paul.
So thank you once again for attending. I hope you found this webinar as fascinating as I did. I look forward to seeing you at the next one from us here at OpenEye's Cadence Molecular Sciences. And until then, goodbye.